In this video, we're going to look at an example of using the limit comparison test to determine if a series converges or diverges. In this example, that series happens to be the sum from k equals 1 to infinity of 2k minus 1 times k squared minus 1 in the numerator, and then over k plus 1 times k squared plus 4 squared. The important thing with trying to use the limit comparison test is you're looking at the terms of the series and see if you can come up with another series that you know by looking at it whether or not it converges or diverges. Okay? That's the main, if you will, challenge in order to solve these types of series problems. So, one of the more common ones that we use are p-series, because we know just by looking at a p-series whether or not it converges or diverges, because all we need to do is determine that power on the n, or k in this case, in the denominator. That tells us whether or not it converges or diverges. So how do we come up with 1 over k squared in this particular example? I'm saying that we need to do a limit comparison test with 1 over k squared. Where in the world did I get 1 over k squared? All right, well, these are polynomials on top and on bottom. We know that as the exponent gets large, a polynomial is dominated by its highest degree term. So what I'm looking at when trying to figure out what these terms of this series are, what I'm trying to compare it to, I'm looking at the highest degree term of the numerator and the highest degree term of the denominator, and dividing those two things. That's how I'm getting this particular series. If you were to multiply out the numerator, you're going to get a 2k cubed as your highest degree term. So in particular, I'm looking at k cubed on top. On bottom, if I multiply everything out, k squared will be k to the 4th, times another k gives you k to the 5th. So as k gets really, really large, this fraction behaves like k cubed over k to the 5th. And that simplifies to 1 over k squared. So that's where that 1 over k squared came from. Now, to apply the limit comparison test, we need to make sure that we have series that have positive terms only. Now, the numerator is a little iffy since we're subtracting, but really we're only subtracting 1, and the k's start at 1 and get bigger. So the numerator here is always going to be positive. Clearly so is the denominator. Also clearly so is our second series here that we're comparing to. So both series have only positive terms. Now we evaluate the limit. So we do the limit of the quotient. Doesn't matter which one you put on top and which one you put on bottom. Do either way. Now, I've got 1 over k squared on bottom, but remember where the 1 over k squared came from. In the numerator, we took the k times the k squared to get k cubed. In the denominator, we took the k times the k to the 4th to get k to the 5th. So that's why I rewrote the 1 over k squared as k times k squared over k times k to the 4th. And now we're just rewriting the fraction with the pieces where they came from, if you will. So taking this k here, I'm writing 2k minus 1 over k. That's where that one comes from. Taking the k squared, I get k squared minus 1 over k squared. Taking the second k here, or the one that's in the bottom, that's where this k plus 1 over k is coming from. And finally, taking this k to the 4th and putting it with the k squared plus 4 squared, putting those two things together. The reason why I put those together now is I can evaluate each of these limits easily. As k goes to infinity, this one goes to 2. This one goes to 1. This one goes to 1, and this one goes to 1. So the whole limit turns out to be 2. Now remember, in your limit comparison test, to be able to make the appropriate conclusion, you need this limit to turn out to be non-zero, which in this case it's not 0, it's 2. So now, whatever one does, the other one does. That's the conclusion of the limit comparison test. Whatever one does, the other one does. So since we have a convergent p-series, 1 over k squared, those terms forms a convergent p-series. The original series must also converge by the limit comparison test.